Connective tissues such as bones, tendons, ligaments, fascia, and cartilage form the essential framework that supports and withstands the physical demands of anaerobic exercise. Each of these tissues adapts in unique ways to the mechanical forces they encounter during activities like weightlifting, sprinting, or other forms of high-intensity exercise. The process of these tissues responding and becoming stronger provides a fascinating look into how our bodies structurally adapt to increased physical demands. When you perform resistance exercises, your muscles pull on the tendons, which in turn apply force to your bones. This force causes slight deformations in the bone, which are primarily bending, compressive, or torsional. When bones experience this mechanical loading, specialized cells called osteoblasts migrate to the bone surface to initiate a process called bone modeling. These osteoblasts produce proteins, predominantly collagen, which lay the groundwork for a strong bone matrix that will eventually mineralize with calcium phosphate, strengthening the bone. The outer surface of bones, known as the periosteum, is where most new bone formation occurs. This helps to increase the bone's diameter and strength. Bone has two types of tissue: cortical, compact bone, and trabecular, spongy bone. Cortical bone forms the dense outer layer of the skeleton, while trabecular bone, which is softer and more flexible, fills the spaces inside. Because of its structure, trabecular bone can respond to stimuli faster than cortical bone, making it more adaptable to exercise-related changes. A critical concept in bone growth is called minimal essential strain, MES, which represents the threshold of force needed to initiate bone formation. When exercise forces consistently exceed this threshold, it signals osteoblasts to strengthen the bone in the areas experiencing the most strain. MES is estimated to be about 1/10 of the force required to fracture bone, creating a margin of safety that prevents fractures while still promoting bone growth. Through progressive overload, continuously increasing exercise demands, activities that exceed MES help increase bone mass and bone mineral density, BMD, making bones thicker, denser, and stronger. The physical forces from increased muscle contractions during anaerobic training lead to greater mechanical stress on the bones, which in turn promotes bone growth and increased BMD. So studies show a positive relationship between muscle strength and BMD. Resistance-trained athletes have significantly higher BMD than their sedentary peers. For instance, studies of professional athletes such as soccer players have shown that bone mass, area, and width may be enhanced even more than BMD due to their rigorous training routines. Bone adaptations occur gradually, taking about 6 months or more to achieve noticeable increases in BMD. However, markers indicating bone formation can be detected within the first few workouts, suggesting that even early training sessions begin triggering osteogenic processes. To maximize bone growth, anaerobic programs should emphasize exercises that load specific skeletal areas, include progressive overload, vary force direction, and involve multi-joint movements. For example, high-impact activities like gymnastics and basketball, which create substantial loading forces, tend to increase BMD more than lower-impact activities. Exercises that directly load key regions like squats and deadlifts are particularly effective for strengthening bones in the hips and spine, areas often prone to osteoporosis. Tendons, ligaments, and fascia are connective tissues that link muscles to bones and support joint movement. These tissues are primarily made up of collagen, a protein that provides structure and strength. There are two main types of collagen in connective tissues: type 1 collagen for tendons, ligaments, and bones, and type 102 collagen for cartilage. In these tissues, fibroblasts synthesize procollagen, which becomes active collagen when the protective extensions on its ends are removed by enzymes. Collagen molecules align into microfibrils, which bundle together into larger fibers and eventually form strong cross-linked collagen bundles, contributing to the strength of tendons and ligaments. Tendons and ligaments, which contain tightly packed parallel collagen bundles, are remarkably strong and resilient, enabling them to withstand the forces generated by muscle contractions. However, these tissues have relatively few cells and limited blood supply, meaning they require less oxygen and nutrients. Their low vascularity also makes recovery slower when they are injured. So, high-intensity exercise is the primary stimulus for growth and strengthening of tendons, ligaments, and fascia. As muscles grow stronger, they exert greater forces on these connective tissues, leading to adaptations that increase strength at tendon-bone junctions within the tendons and ligaments themselves and in the fascia surrounding the muscles. These adaptations include increased collagen fibril diameter, more cross-links within collagen fibers, an increased number of collagen fibrils, and denser collagen packing. All of these changes help connective tissues withstand higher forces. Studies show that tendon stiffness, the force transmission per unit of elongation, increases with resistance training. In one study, a group experienced a 15 to 19% increase in Achilles tendon stiffness after 8 weeks of heavy load training, but there was no change with light loads, 20% of 1 RM, emphasizing that only high intensity loads significantly impact tendon adaptation. Cartilage is a dense, resilient tissue that cushions joints and absorbs the forces that travel through them. It plays several roles in the body, including creating smooth joint surfaces, absorbing shock, and aiding in the attachment of tendons and ligaments to the skeleton. Unlike other connective tissues, cartilage lacks its own blood supply and relies on nutrients from the surrounding synovial fluid. This is why cartilage is slow to heal after injury. Cartilage comes in two main types related to physical activity: hyaline cartilage, which covers joint surfaces, and fibrous cartilage, found in areas like intervertebral discs and tendon attachment points. The movement of joints during exercise is essential for cartilage health, as changes in pressure drive nutrients from synovial fluid into the cartilage, promoting cell health and structural integrity. Studies show that immobilization leads to cartilage degradation because essential nutrients are not diffused effectively, which causes the death of cells within the cartilage and the breakdown of the cartilage matrix. Although cartilage undergoes atrophy without loading, the effects of increased external loading on cartilage thickness are still not fully understood. Current research suggests that moderate intensity exercise may be adequate to maintain cartilage thickness, and that strenuous exercise, when progressively overloaded, does not necessarily lead to joint damage. To effectively stimulate adaptations in connective tissues, training programs should consider the following principles. For tendons, ligaments, and fascia, use high-intensity loading with progressive resistance. Incorporate exercises that apply forces throughout a joint's full range of motion, emphasizing multi-joint exercises over isolated single-joint movements. For cartilage, moderate intensity anaerobic exercises are generally sufficient to promote cartilage thickness and joint health. A variety of exercise modalities helps maintain tissue viability by ensuring nutrient diffusion and proper loading across the joint's full range of motion. In summary, connective tissues play a vital role in supporting the body's response to anaerobic exercise. Bones become denser and stronger in response to the forces generated during exercise. Tendons, ligaments, and fascia adapt by increasing collagen strength and density to handle increased muscle strength. Cartilage, while more challenging to train directly, remains healthy with regular joint movement and moderate loading. By understanding these tissue-specific adaptations, athletes and coaches can design more effective training programs that not only build muscle strength but also fortify the body's structural foundation for improved performance and reduced injury risk.